All right. Thank you very much. So yeah, here we go. There we go. Okay, great. So hi, everyone. My name is Andrew Graus. I'm a graduate student at the University of California, Irvine. And I'm going to talk to you today about, what do we measure when we measure star formation histories? I'm actually going to go back to this morning session. I'm talking about dwarf galaxies specifically. And I'm also specifically going to be talking about measurements of star formation histories with space telescopes like HST and then future telescopes. So this is work that I'm doing with my advisor, James Bullock, and all of these really nice people who I've listed down below. Okay, so let's start. So this picture has been getting a lot of show during this conference, but this is Fornax. It is a dwarf galaxy in the local group. It has a stellar mass of about a few times 10 to the 7, and it has a half-light radius of about 700 parsecs. If I was to draw it really roughly in Keynote, this is what it would look like. Now, if you were to give me a space telescope, I don't know why you would do that, but if you were to do that and say measure the star formation history of this galaxy, well, it turns out how big would HST's field be in this picture, right? So it turns out if you were to do this, it would look like this. It's about 1% of the area within the half-light radius. Now, if we were to step back and take the whole local group in context, this is the galaxies from Dan Wise's 2014 sample of star formation histories with HST, archival HST data. And this is the fraction of the area within the half-light radius that one HST field covers. And what you can see is for galaxies really far out, it is all right, on the order of tens of % for most of the galaxies, but really close, particularly for the classical dwarfs of the Milky Way, because they're so big and so close, you're on the order of 1% here. So the thing that's been bothering me and the thing that I've been thinking about for the past few months is, can you extrapolate star formation histories of local group galaxies to the entire galaxy, and can you do this reasonably? Now, the reason that you might want to do this is if you're, say, measuring quenching times for galaxies, or if you are doing something with the fossil record, like trying to use the local group to extrapolate properties of high redshift galaxies, or even if you have simulations and you want to see if they, correspond to the real galaxies, right? So how am I going to go about doing this? How am I going to go about testing this? Well, I'm going to use fire simulations. We've heard a lot about fire so far at this conference, so I'm not going to belabor this point. But I'm going to use dwarf galaxies. This is one of the little guys down here. And so for my purposes, they create galaxies with stellar properties, the stellar distributions both in space and time, that look basically what we think real galaxies should look like. Specifically, I'm going to be using galaxies run by Alex Fitz. This is the same sample that Alejandro used this morning. And this is where they lie on the stellar mass-halo mass relation. This is here are these magenta triangles. I myself am running some additional higher mass dwarf galaxies. This is where they are on the stellar mass-halo mass relation. These are the low-res runs, though. The final resolution runs are running as we speak. So I'm going to exclude them from the rest of this analysis, but just so you know that those simulations are coming. Now, how am I actually going to test the star formation histories? Well, at first, I'm not even really going to worry about the entirety of the galaxy. I'm going to focus in on the stellar half mass radius. I want to know if we can even get that right. So the way I'm going to do this is I'm going to break up the area within this should be the half mass radius, not the half light radius. The area within the half mass radius up into 100 fields, and then measure the variance of the star formation history as a function of % coverage of the area within the half mass radius, okay? So basic schematic of how this works is, here's the center of one of these galaxies. This is M12M, or M10M, sorry, and it has a stellar mass of a few times 10 to the 7, or 1 times 10 to the 7. This is the star formation history of everything. If I restrict myself to the stellar half mass radius in projection, this star formation history looks like this, right? Okay, so then I'm going to divide it up into a grid, 10 by 10 grid, 100 fields. And then I'm going to say, okay, if I was to measure this star formation history, where would I put my field? Let's say I only get one shot at this. Well, I'd put it right at the center, right? Because that's where most of the stars are. But it turns out that the star formation history of that is like this. It's a little bit later forming. So let's say, okay, I was a little bit overzealous. Let's try again. Let's pick something further out, like way out here. just beyond this projected stellar half mass radius. And when I do that, I get this. It's way older. And so what's interesting, and the reason for this is because kind of Phil touched on this yesterday, but these have very strong age gradients. The inner regions are younger and the outer regions are older. So if I'm measuring the star formation history of these things, and I'm not careful about where I place my field, I can get it pretty wrong. All right? So one thing that I might be thinking about is, okay, what is like some time parameter, like T90, the time that it takes each star formation history to reach 90% of its mass, right? This is a metric that's often used for quenching, but I don't know this is really applicable for that because these are all star-forming galaxies. These are still star-forming at redshift 0. They're isolated. But let's just say, okay, well, what's the total variance in the star formation, this time parameter, T90, as a function of coverage fraction? When I do that, it looks like this. This is for all of the simulations in Alex's suite, normalized to their actual value of T90, right? And so at 100%, well, I get it correct, right? Obviously, by construction. But if I'm down here at like 1, 2, 3%, I can get pretty large errors on the order of 10 to 20%. Now, the normalization of this is something like 10 gigayears, so this corresponds to an error of about a gigayear, right? And this is where some actual galaxies would lie in this space. So for real galaxies, you could have a pretty significant deviation in your star formation history. So then the next thing I want to ask is, can we do better? So I was being pretty dumb and doing things randomly, but do we have to be random, right? Can we do better? Now, you might remember this plot, and you might say to yourself, like I did, well, if the inner regions are too young and the outer regions are too old, is there a radius in the middle where you get it right? Turns out, yes. Duh. And so what I did to kind of figure this out is I just sort of binned things in projection, radially in projection. And I constructed these bins such that there was the same number of particles in each of these bins. And so they're colored on the left here, what the bin is, and they're colored by their radial projected distance away from the center. So obviously, the ones very close are young, the ones very far away are old. This red is the total, right? Now I'm worried about the total star formation history. And it turns out that this radius that matches this pretty well is actually pretty close to the stellar half mass radius, right? And it's basically because you're playing a game. You're doing a magic trick where you have this distribution of stars within the galaxy that has some mix of young and old stars. And I want to find the radius where I get that same mix in a smaller area, right? So what I can do now is do something simpler, like just place 6 fields at this radius. See what happens. What's the star formation history of that look like? Well, it's actually pretty close to the true star formation history of the entire galaxy, not even the area within this projected stellar half mass radius. And so for, relatively simple, short amount of time, I can get a pretty accurate answer. So why do we care? Well, we care because we care about our telescopes. And specifically, very soon we'll have 2 new telescopes coming online, one James Webb and one in the further distant future, WFIRST. And they're going to be pretty good for measuring star formation histories. But we need to think a lot about how we want to go about measuring the star formation histories of these galaxies. James Webb is going to have a field of view similar to Hubble. So you might think, okay, maybe we can just place a few fields at around the stellar half mass radius and get the star formation correct. Or do we have to wait for WFIRST? The thing about WFIRST, the great thing about WFIRST, is it has this massive field of view, right? And so you'll be able to measure most of all of the dwarf galaxies of the local group just with this telescope. But there's going to be a lot of people that want to use this as well. The telescope's going to be very oversubscribed. So we need to think very specifically about how we want to use it. So I'm going to end with some takeaways. I think that there's a large amount of power locked up in the star formation histories of the local group. If you just care about quenching, or if you care about, investigating the fossil record, seeing what we can learn about the high redshift universe from nearby galaxies. However, uncertainties from incomplete coverage can significantly impact your results, especially if you don't know how to account for them, if you're just kind of randomly putting your fields But I think by being smart about how we place these fields, we can get accurate star formation histories, and we can be efficient with telescope time. That's it. Thank you very much. Yes, exactly. So this seems to be pretty robust for the galaxies in Alex's sample, that you get accurate star formation histories at basically this projected stellar half mass radius. But yeah, it's not clear how this translates to satellite galaxies, right? Or even higher mass galaxies, maybe where you have a larger contribution from accreted stars, something like that. We're not sure. I hope that it's true, but it's something that we're going to investigate in the future. Absolutely. Absolutely. That would be phenomenal. So you could think about reversing this and saying, so one of the things about these galaxies is this age gradient is set by some combination of stellar feedback and sort of inflows and outflows. So you can imagine doing the reverse and planning a bunch of star formation histories and getting a constraint that way. I absolutely agree.